Good day everyone, I'm Joanna Garama and I will be talking about titrometric analysis or titration. So let's go. First, what is titrometric analysis? It is a quantitative and volumetric technique to determine the unknown concentration of a solution by the known concentration of a solution in the presence of an indicator, or it can also be called as titration. Quantitative chemistry is concerned with figuring out how much of a component or components is present in a sample. The titrometric analysis is one technique utilized in this determination to attempt to provide a response to the question, how much? In the laboratory, we frequently gauge the volume of one solution needed to react with a certain volume of a different solution whose concentration is only known, and then the concentration of the other solution is then determined. Or in short, titrations are analytical techniques we can use to quantify the amount of the desired substance present in a given sample. Titration is the procedure in which a solution of one reactant, the titrant, is carefully added to a solution of another reactant, and the volume of titrant required for a complete reaction is measured. The concentration of one solution, usually but not necessarily the titrant, is known. This allows one to calculate the concentration or the amount of reactant in the other unknown solution, using the known reaction ratio. A typical laboratory technique for applying quantitative chemical analysis is titration. This technique is used to ascertain an unknown analyte's concentration. Volumetric analysis, the measuring of volume, is very crucial for titration technique and method. A feasible titration requires that, first, the reaction between standard and analyte has to be known. Second, the reaction between the reactant is reasonably fast. Third, the reaction proceeds quantitatively to completion. And last, there must be some method or substance available to detect the endpoint. The exact concentration of a solution is determined using a process called standardization. A primary standard is accurately weighed, dissolved, and then titrated with the solution until the endpoint is reached for standardizing solutions. The main standard is a highly pure, stable solid with a high molecular weight that undergoes a non-chemical reaction when it comes in contact with the solution to be standardized. Now let's talk about the difference between aqueous titration and non-aqueous titrations. Aqueous titrations use water as a solvent for dissolving the analyte samples for the titration, whereas non-aqueous titration use organic solvents for dissolving the sample. An example of an aqueous solution is a salt solution where the solute is salt and the solvent is water. The non-aqueous solutions are defined as the solution where the solvent which is used is other than water. The objectives of the titration technique or the titrometric analysis is to find the equivalence point, which is the point where chemically equivalent quantities of the reactants are combined. Titrating a simple solution with the volume of a regular acid solution of a known concentration needed to neutralize it may be used to determine its concentration. Nowadays, due to the increase in demand, the classical method of titration in the industrial sector has been replaced by auto-titrators, machines that progressively feed in the titrant and measure whatever property is used to determine the endpoint. Nonetheless, manual titration is still proved very useful where the cost or need for automation is not justified. For instance, titration in the chemistry laboratory serves as a bridge between several theoretical concepts and practical operations for students pursuing chemical sciences or engineering. It gives practice in balancing equations and the relevant mathematics to convert between volume, mass, and mole, which is very vital for both disciplines. It is also beneficial to food industry, cosmetic industry, wine industry, pharmaceutical industry, and many other industries that can be very beneficial to us.
Hello, I am Alea Enriquez and I will explain how titrometric analysis works, including the calculations involving molarity and titration. My topic will be a big help before identifying the types and experiment of titrometric analysis. So first, let's compute the most common time or way to express solution. The concentration is molarity, which is defined as the amount of solute in moles divided by the volume of solution in liters, is equal to a moles of solute or liters of solution. And here, the example of it. As you can see in the presentation, we have a container that we are going to dissolve the sodium sulfate in water, and the sodium sulfate is solute and the water would be solvent. The total volume of solution is 250 milliliters of solution, and the solvent, which is the H2O or the water. We all know that we have 35.5 grams of sodium sulfate. And so given this information, how do we figure out the molarity? We need to look at the molar mass that we can see in the periodic table. So the molar mass of sodium sulfate would be 142.04 grams per mole. So as you can see in the presentation, figure out the molarity of this solution. What's the molarity of the sodium sulfate in this solution? First, we're gonna figure out the number of moles of solute. So the mass would be 35.5 grams of sodium sulfate. So we need to multiply, and that would be cancelled out the grams. So for every 1 mole of sodium sulfate is 142.04 grams of sodium sulfate. And cancel it again, and we're left now the moles of sodium sulfate. So now to figure out the molarity, divide by the liters of solution, which is 0.250 liters of our solution. So we have 3 significant figures of that answer, and the final answer will be 1.00 moles. A typical setup for titration in a teaching laboratory, the solution to be titrated is placed in a Erlenmeyer flask and a few drops of indicator are added. So the burette is filled with a standard solution or the solution to be standardized. The volume of solution in the burette is read carefully. The meniscus describes the surface of the liquid in the burette. Aqueous solution sweat glass, so the meniscus of an aqueous solution is always concave. The position of the bottom of the meniscus is read and recorded. The solution in the burette is added dropwise near the endpoint, with steering to the Erlenmeyer flask until the endpoint is reached. The endpoint is signaled by the appearance or change of color throughout the solution being titrated. The volume of the liquid is read again. The difference between the final and initial burette reading is the volume of the solution.
Good day, I'm Alessandra Uson, and I'm going to talk about the calculations for acid-base titrations. An acid-base titration is a quantitative analysis for precisely neutralizing an acid or base with a standard base or acid solution of known concentration. So, we are going to do first the standardization of acid solution and the standardization of base solution later. So, for the standardization of acid solution, calculate the molarity of a solution of hydrochloride if 50 ml of the solution neutralizes 0.475 grams of potassium hydroxide. We first write the balance equation. So, hydrogen chloride plus potassium hydroxide, the products of it is potassium chloride plus water. So, the equation is already balanced. If there is 1 mole of hydrogen chloride, there is also 1 mole of potassium hydroxide. We know from the balance equation that 1 mole of hydrogen chloride reacts with 1 mole of potassium hydroxide, which is 56.1 grams. This provides the reaction ratio that converts 0.475 grams of potassium hydroxide to the corresponding number of moles of hydrogen chloride, from which we can calculate the molarity. So, calculating this, unknown mole of hydrogen chloride equals to 0.475 grams potassium hydroxide times 1 mole potassium hydroxide over 56.1 grams potassium hydroxide times 1 mole hydrogen chloride over 1 mole potassium hydroxide would give us an answer of 0.00847 mole hydrogen chloride in which present in 50 ml solution. So now we are going to calculate the molarity of the hydrogen chloride. Unknown mole of hydrogen chloride over liters equals to 0.00847 mole hydrogen chloride over 0.05 liters, in which the 50 ml is converted to liters, and that is 0.05 liters. So the answer would be 0.1694 mole hydrogen chloride. Now, I am going to discuss the standardization of base solution. A 30 ml sample of a solution of sodium hydroxide reacts with 0.4215 grams of potassium hydrogen phthalate. Calculate the molarity of the sodium hydroxide solution. So, we first write the balance equation, which is sodium hydroxide plus potassium hydrogen phthalate. Then the products would be sodium potassium phthalate plus water. 1 mole of sodium hydroxide would react with 1 mole of potassium hydrogen phthalate. 1 mole of potassium hydrogen phthalate is 204.2 grams. Then we are now going to calculate the number of moles of sodium hydroxide in 30 ml of solution from the amount of potassium hydrogen phthalate that reacts with it. Unknown mole sodium hydroxide equals to 0.4215 grams potassium hydrogen phthalate times 1 mole potassium hydrogen phthalate over 204.2 grams potassium hydrogen phthalate times 1 mole sodium hydroxide over 1 mole potassium hydrogen phthalate. That would give us an answer of 0.002061 mole sodium hydroxide. So we will calculate now the molarity of the sodium hydroxide solution. Unknown mole sodium hydroxide over liters equals to 0.002062 mole sodium hydroxide over 0.03 liters sodium hydroxide would give us an answer of 0.0687 mole sodium hydroxide. That's all for my topic, calculations for acid-base titrations.
I am Joy R. Castillo, and I will be discussing one of the types of titrometric analysis, which is redox. Ever heard of redox? Well, redox reaction is a type of chemical reaction that involves a transfer of electrons between two species. The term redox is made up of two words, which are reduction and oxidation. The gains of electrons by a substance is called reduction, while the loss of electrons by a substance is called oxidation. Always remember the general rule, which is when an oxidation number increases, this is oxidation. When an oxidation number decreases, this is reduction. Oxidation number is the number that is allocated to elements in a chemical combination. And for that, I'll explain it further by examples and also take note of the certain rules when it comes to obtaining oxidation numbers. First rule, for an atom in its elemental form, the oxidation number is always 0. And second rule, for any monatomic ion, the oxidation number equals the ionic charge. For example, here we have iron and the oxidation number is 0 because it is stated in the first rule. Then we have aluminum cation and the oxidation number is the ionic charge of it, which is +3. Then for our third rule, non-metals usually have negative oxidation numbers, although they can sometimes be positive. The oxidation number of oxygen is usually -2 in both ionic and molecular compounds. The major exception is in compounds called peroxide, which contain the oxygen 2 and -2 ion, giving each oxygen an oxidation number of -1. Then the oxidation number of hydrogen is usually +1 when bonded to nonmetals and -1 when bonded to metals. The oxidation number of fluorine is -1 in all compounds. The other halogens have an oxidation number of -1 in most binary compounds. When combined with oxygen, as in oxyanions, however, they have positive oxidation states. So, for our example, the substance is H2O or water, and the oxidation number is hydrogen equals +1 and oxygen equals -2. Then we have hydrogen peroxide with oxidation number of hydrogen equals +1 and oxygen equals -1. And here we also have a substance that is bonded to fluorine with oxidation number of oxygen equals +2 and fluorine equals -1. For the last example, we have hydrogen bonded to metal and with oxidation number of sodium equals +1 and hydrogen equals -1. For the last rule, the sum of the oxidation number of all atoms in a neutral compound is 0. The sum of the oxidation numbers in a polyatomic ion equals the charge of the ion. This example shows chloride as a substance, and for the oxidation number, we are finding the chlorine's oxidation number by multiplying the charge of the chloride to the oxygen, which will be -2 times 3 equals -6, and for the overall charge is equal to -1. And we now have the oxidation number of chlorine, which is +5 or +5. Now we can have an example of the redox reaction and how we will balance and identify all of the elements if they are oxidized or reduced. This is also called oxidation reduction reaction if you prefer a longer term. So here is the redox reaction example. And we can see that the copper is changing from 0 to +2, while the silver is changing from +1 to 0. And for both sides, we have nitrogen which is equal to +5 and oxygen which is equals to -2. Well, nitrogen is part of nitrate, so it's not changing the nitrogen and oxygen. In our conclusion, this is indeed a redox equation because copper is oxidized and silver is reduced. That's all, and thank you for listening.
Hi, my name is Joshua Dudulao, and now that we are done with the definition of the meaning of titrometric and also with the types and how titrometric analysis works, let's now proceed sa experiment for us to further understand our topic, which is titrometric analysis. So, in titrometric analysis, a solution of known concentration, the standard, is made to react with a substance being analyzed, the analyte, and then the standard, which is usually the titrant, is added in small increments to the analyte solution using a burette until an indicator in the solution gives a sharp color change signaling the endpoint. So that endpoint was only discussed natin siya later during the experiment then. So that endpoint, it coincides or really coincides with the equivalent point, which is the point when an equivalent amount of the titrant has already been added to react completely with the analyte. And then we have indicator. Indicator is a substance which changes in color depending on whether the solution is acidic or basic. So an example of an indicator is phenolphthalein, which changes its color from colorless sa acidic solution, and then pink naman siya kapag nasa basic solution lang siya, yung basic solution. So for this experiment, for this titration experiment, it involves acid-base neutralization to determine the amount of acidic compound or component rather in soft drink and vinegar samples. So we need our apparatus and materials. So first thing we need for this experiment is 50 ml acid burette lamp, iron stand, 250 ml Erlenmeyer flask, 10 ml measuring pipettes or pipettes, potassium hydrogen phthalate, 0.10 m sodium hydroxide, 1% phenolphthalein, white vinegar sample, and our colorless soft drink sample. So after natin ma-complete yung mga kailangan nating apparatus and materials, mag-proceed naman na tayo sa ating first step na ating pag-experiment. So the first thing we need to do is to prepare our burette. So rinse a previously clean burette with approximately 4 ml of triton solution to allow some of the liquid to run through the tip of the burette or the burette, and then repeat the rinsing process 2 more times, discarding the sodium hydroxide used each time, and then fill the burette with 0.10 m sodium hydroxide, taking care that no air bubble is trapped in the space below the stopcock, and then clamp the burette onto an iron stand. So may iron stand tayo, doon natin ka-clamp, and then adjust the volume reading to or below the 0 mark, and then touch the tip of the burette to the side of the beaker to remove any hanging drop, and to allow the solution to stand and to stand for a few minutes and observe na lang din for any leakage na pwede mangyari. And after that, look at the lower meniscus of the solution in the burette at eye level, and then read and record the initial volume of the solution. And then second step we need to do is ito na, mag-proceed tayo sa standardization of sodium hydroxide. So take note of the weight and the percentage of purity of the pre-weighed KHP in the Erlenmeyer flask, and then add about 70 ml of the given distilled water, and then swirl to mix and dissolve the solid. And then after that, add 3 to 4 drops of phenolphthalein indicator, and then titrate it. And then titrate it with the sodium hydroxide solution of unknown concentration until the solution gives a permanent faint pink color. So ayun yung kailangan imagine because ito yung endpoint ng ating titration. Then after nun, i-record natin yung final volume of the solution dun sa ating burette, and then do another trial, and then after nun, iti-take note natin kung ano yung initial and final volume ng ating solution dun sa ating burette. Then after nun, sabi dito, solve for the average molarity of the sodium hydroxide solution and express it in 4 significant figures. So, the next step, magpupusin naman tayo sa ating mga samples. So, sa step 3 and 4, vinegar and soft drink samples. So, for the third step, it is the analysis of acetic acid in a vinegar sample. So, we need to pipette 1 ml of white vinegar into a clean Erlenmeyer flask and then dilute with approximately 50 ml of distilled water and then add 3 drops of phenolphthalein indicator. So we need to swirl to mix and then titrate with the standard sodium hydroxide until the endpoint is reached. So remember na yung color na kailangan natin ma-achieve doon, be careful na baka ma-over-titrate natin yung ating vinegar din. Then remember to record the initial and final volumes of the solution in the bread and then do another trial. After that, calculate the average molarity of acetic acid in the vinegar sample and then express the answer in 3 significant figures using the average molarity of sodium hydroxide obtained in the standardization step. So, I'm going to show you a clip na related dito sa ating vinegar sample na step. So, let's watch this.
Today we're going to do a titration of vinegar. So we have 5% vinegar solution. We have distilled water. We have 0.1 molar sodium hydroxide solution. We have our phenol in here. We have my flask. And our pure 2 filled with sodium hydroxide. So let's begin the titration process. Okay, I'll start by adding 5 milliliters of my vinegar solution. So you can type better. I've got 5 milliliters of vinegar. So make 2 5 milliliters of light. And I will add that to my flask. To that, we will then gather 20 milliliters of distilled water. So I will gather 5 milliliters. And we'll do that 4 times. So 1. And gather another 5. And I will gather another 5. And the last set of 5 is 20 milliliters. 25 milliliters solution, 5 milliliters there, and 20 milliliters water, and to that we'll add 5 drops of phenolphthalein solution. Now let's talk a little bit, but it's rolling out. It will clear because phenolphthalein is clear in acid solution. And now we will begin the titration process by adding some sodium hydroxide to our acid solution. You will notice that we are going to start seeing pink, and as we swirl it, the pink will disappear. So we will add it at a little faster rate. See the pink forming, and we'll swirl it and notice the pink goes away. And our job as we titrate is to bring it to a point where the pink color holds, even though you may swirl it. Point of our titration. And now we're going to read the amount of NaOH that we use in this titration, and that gives us a 44.4 milliliters, reading 44.4 milliliters.
So yeah, almost same process. Pinakita rin also yung kung paano prepare yung ating mga apparatus and other materials doon sa ating pagsasample dito, pag-titrate dito sa ating vinegar sample. So it is important talaga yung maayos sa atin yung mga apparatus natin para sunod-sunod din yung process natin. And of course, kailangan natin record yung ating yung pagka-titrate dito sa ating vinegar. And then sa last part ng video, nakita rin yung pagka-calculate ng mga kailangan natin like yung molarity of the acetic acid doon pinakita rin sa video. And then, fourth step, yung analysis naman ng carbonic acid doon sa ating soft drink sample. So, we need to prepare 20 ml of soft drink into a clean Erlenmeyer flask. Almost same step kanina, tulad dun sa ating vinegar sample. We also need to dilute with approximately 50 ml of distilled water and then add 3 drops of phenolphthalein indicator. And as well to mix and with the standard sodium hydroxide until the endpoint is reached. Then remember to record the initial and final volumes of the solution in a bread and then do another trial. So I'm gonna show you again po na almost same video nito na papakita natin. So let's watch this.
Right, second one is 7 up, the third one is seltzer. I got 5 mils, 5 mils, 5 mils. In each one I'm going to put drops of phenolphthalein, which is an indicator. So 2 drops in the first one, 2 drops in the second one, and 2 drops in the third one. Again, the first one I'm going to titrate is Sprite. The second test tube is 7 up, and the third test tube is full of seltzer. So we have sodium hydroxide, which is a base. So I'm going to count the drops and continue to swirl it. So 6, 7, 8, 9, 10, 11, 12, 22, 23, 24, 25, so it's going to take pink, we're going to do slow, 26, 27, 28, 29, 30, 31, 32, 33, so pink color stays around for a while. We're going to count that as 33, I'm just going to try one more to see what happens. 34. So maybe 34, that pink color stays. That was the Sprite. Maybe the which we'll see. And then I'm just going to add 1, 2, 3, 4, 5. I want to show you what it means to titrate. That's what it looks like when you over titrate. So that white pink I've now turned that into a base. So that was 34, 35, 38. So I'm getting at 27, 24.
After one, we need to calculate the average molarity of carbonic acid naman in the soft drink sample and then express the answer in 3 significant figures and then use the average molarity of sodium hydroxide obtained in the standardization step. So doon sa video na naipakita kanina, di ba sabi natin kanina during pag-explain natin ng mga apparatus and materials na kailangan natin, we need a colorless soft drink sample and then gumamit doon ng colorless soft drink sample which is Sprite. So kailangan natin ng colorless sample kasi kapag may color yung soft drink na gagamitin natin, mas mahirap para sa atin na may observe and makita yung pagka-titrate na kailangan natin. Pahirapan natin makita yung endpoint na kailangan natin ma-reach. Kasi, for example, gumamit tayo ng Royal or ng Sprite, ng Royal or ng Coke. Eh, di ba, ang color nila is different. Orange and black or something brown, something like that. Mas mahirapan tayong may observe yung pag-iiba ng kulay. Yeah. So, we need a colorless sample of something para mas madali natin makita yung pag-reach niya ng endpoint. So, yeah. So, yan, hindi lang naman doon natatapos yung process ng pag-experiment natin. Kasi after nun, may mga observation pa mangyayari, like, kung anong nangyayari doon sa ating mixture, so on and so forth. And after natin mag-experiment, of course, mag-proceed tayo sa waste disposal. We need to dispose our wastes properly. Kasi, of course, gumamit din tayo ng mga chemicals or mixtures na pwedeng magpahamak sa mga kasama natin and to our environment, of course. So, the first step is dito sa mag-experiment natin na kailangan natin gawin for disposal is to collect the sodium hydroxide rinsings into a beaker and then dilute with plenty of water and then flush directly down the sink with copious running water. Second, dilute all diluted solution with plenty of water and then flush directly down the sink with copious running water. So, kaya naman natin na after experiments, pababayaan lang natin yung ating mga ginamit, yung mga chemical and other samples na ginamit natin doon lang sa table kasi tendency is pwedeng mag-inito, matapon bigla or pwedeng may gumalaw noon. Magdamasan pa kung may minute na doon sa sobrang pagkakulit. After